Welcome to the class. Dear students, today we are going to see what are conjugated dienes, what is the reason of exceptional stability in conjugated diene, and we will also look into addition reaction of conjugated dienes. So let us start conjugated dienes. So conjugated dienes are alkadienes. Alkadienes means alkenes with two double bonds. So they are alkene with two double bond, but the two double bonds, they are separated by a single bond. Correct? The two double bonds, they are separated by a single bond. So that is a conjugated diene. An example of conjugated dienes are 1,3-butadiene. You can see two are separated by 1. 2-methyl-1,3-butadiene. Here also 2 is separated by 1. 1,3-pentadiene. 2 are separated by 1. So alkadienes in which two double bonds are separated by one single bond, they are referred to as conjugated dienes. There is another way of explaining conjugated diene. What is that other way? Alkadienes in which double bonds and single bonds are arranged in alternating fashion along the carbon chain. What did I say? Alkadienes in which double bonds and single bonds are arranged in alternative fashion along the carbon chain. So such kind of dienes are called as conjugated dienes. We have seen 3 examples of conjugated dienes. Now the question is, look at the 1,3-butadiene. Let us see 1,3-butadiene, that is the simplest of all conjugated diene. Let us see. What is it made up of? It is made up of two double bonds, right? So it is having how many pi electrons? 4 pi electron, correct? Right, guess. It has got 4 pi electron. So that makes it very rich electron species, right? So that is a very rich electron rich species. Who would attack that? Who would attack it? A electrophile can easily attack it, right? And that would make the conjugated diene, here in this case 1,3-butadiene, very reactive. Because it's very reactive. Why? Because it has got 4 pi electrons. It is electron rich species. It is rich in electrons. So any species that wants electron, like an electrophile, can easily attack. That would make it very reactive. That would make it very unstable. However, that is not the case. Alkadienes are very stable. They are very unreactive. What makes them stable? What makes them unreactive? That is what we are going to look at now. So for explaining its stability, let us again look at the structure of your 1,3-butadiene or conjugated diene. Now each carbon, be it this carbon, this carbon, this or this, each carbon is doubly bonded carbon atom. A doubly bonded carbon atom is actually which hybridized? Right, sp2 hybridized carbon atom. sp2 hybridized means that there are one s and two p orbitals have mixed and merged with each other in the process called hybridization, and they have produced 3 sp2 hybrid orbitals, right? They produce 3 sp2 hybrid orbitals, correct? And these 3 hybrid or sp2 hybrid orbitals, how do we account it for? Let me account it for like this. These are the, see, 3, 4. So these are the sp2 hybrid orbitals. This is overlap of sp2 hybrid orbital with sp2 hybrid orbital of this carbon. This is the overlap of sp2 hybrid orbital of this carbon and sp2 hybrid orbital of this carbon. So they make sigma bonds. So the sp2 hybrid orbitals, they overlap with each other. The carbon's sp2 hybrid orbital, they overlap with each other to form carbon-carbon sigma bond, and they overlap with s orbital of hydrogen to form carbon hydrogen single bonds, sigma bond. They overlap with s orbital of hydrogen atom to form carbon hydrogen sigma bonds. So what we have seen that the three sp2 hybrid orbitals. They overlap with each other. The carbon's sp2 hybrid orbital, they overlap with each other to form carbon-carbon sigma bond, and they overlap with s orbital of hydrogen to form carbon-hydrogen sigma bond. Now there is one more p orbital, am I right? There are no two p orbitals, there is three p orbital. Only two have mixed with one to form sp2 hybrid orbital. There is one more p orbital which is unhybridized. Unhybridized. It has not taken part in hybridization. Let me write like this. So it is unhybridized. And this unhybridized p orbital, they have one electron. Am I right? They have got one electron, and electron can be anywhere. We don't know where the electron is. I have written a dot here, but actually electron can be anywhere. It has got one electron. What is the option with carbon to fulfill its fourth valency? Right? Three valency has been fulfilled. Now carbon has to fulfill the fourth valency. There is fourth valency here. What is the option with carbon? There is no other hydrogen. What is the option with carbon? The option with carbon is to go for sideways overlap. To go for sideways overlap of the p orbital. If sideways overlap of p orbital occurs, then pi bond is formed. What are the options available? This is carbon 1, 2, 3 and 4. What options are available? Let us see. Carbon 1 p unhybridized p orbital can overlap with carbon 2's unhybridized p orbital. Carbon 4's unhybridized p orbital, it can overlap with carbon number 3's unhybridized p orbital. Carbon number 2 unhybridized p orbital, it can overlap with carbon number 1, as well as it can overlap with carbon number 3's unhybridized p orbital. And carbon number 3, it can overlap its unhybridized p orbital, it can overlap with carbon number 4 and carbon number 2's unhybridized p orbital. So here is the net output. See carbon number 1's unhybridized p orbital, it has to fulfill its fourth valency. Three valencies have been fulfilled. Fourth valency, how it will fulfill? The only option here is to go for sideways overlap. So the carbon number 1, it can overlap with carbon number 2's. Carbon number 4's can overlap with carbon number 3's. Carbon number 2 has two options. It can go like this and it can go on the right side. And carbon number 3 also has two options. Either it can go for the right side and it can go for the left side. So this causes continuous flipping of p orbitals. There is a continuous flipping and there is continuous, like two hands clapping. So this goes for continuous flipping of your p orbitals, and that would result in what? That would result in what? That would result in, let me draw this one. So that would result in delocalization of pi electrons over a large surface area. See, if there is continuous flipping of p orbitals, one combines with 2, then 1 leaves 2, and then 2 combines with 3, correct? Similarly, 3 combines with 4, 3 leaves 4, and 3 combines with 2. So that leads to continuous flipping of p orbitals here and there on the left and right side. So this kind of motion is set, correct? And that leads to delocalization of pi electrons above and below the plane of the molecule. And the main thing is the delocalization of the pi electron is extended over a large surface area, correct? And that gives immense stability to conjugated dienes, and particularly here speaking 1,3-butadiene. Right? Now it would be very difficult for an electrophile to attack the electron because the delocalization is over a large area, and it's very difficult to find an electron from this large area. Had it been a shorter area, electrophile would have been easier. It would have been easier to find. But now it's a large area and it's very difficult for the electrophile to find an electron here. right? So this delocalization of the pi electron over this large area brings immense stability to conjugated diene. Dear students, that finishes the conjugated diene, and also it finishes the stability of conjugated diene. Why it is stable we have discussed. Now let us understand the addition reaction of conjugated dienes. So conjugated diene is, of course, it's an alkene, and being an alkene, it's actually two alkene, right? Alkadiene, and being an alkadiene, it should go for addition reaction. What would get added? An electrophile would get added because it's rich in electron. I agree it is stable, but that is a reaction it would show ultimately. So it can undergo addition reaction with your halogens, okay. It can go addition reaction with HBr, HCl. It can go addition reaction with H2 in the presence of a catalyst, of course. So let us see its reaction with Br2, fine, and we will understand the addition. Let me take 1,3-butadiene. This is 1,3-butadiene. Right? And let me add it to bromine. Take a solvent CCl4 so that polarization of Br plus and Br minus comes out. So that in CCl4's presence that would come out. It would be split as Br plus and Br minus. And now what would happen? Because electrophile will first get added. That is Br plus would first get added, and after that Br minus would get added. That would lead to two products. One is the 1,2 addition product and the second one is the 1,4 addition product. Let us see. So the first one is the 1,2 addition product, which I have almost drawn. This is the 1,2 addition product. 1,2 addition product. And the second one that you get is 1,4 addition product. This is the 1,4 addition product. So you can get two addition products, the 1,2 adduct and 1,4 adduct. Now because this is rich in electron, the electrophile gets added, Br plus first gets added and Br minus later gets added. Okay, and two products are formed, 1,2 adduct and 1,4 adduct. Now why 1,2 addition product and why 1,4 addition product? Why does this happen? For this we have to go through its mechanism. To go for its mechanism, let me take HBr as the reagent. I will take HBr, not Br2, so that it is much easier to understand and distinguish between the electrophile and the nucleophile. Okay, let me take HBr as the example. So step number 1, HBr, I will write the reaction first so that you get the idea. This is the your 1,3-butadiene. This is HBr. If you reacted, what would happen? The first product that you get is like this. So that will be CS3, CH, and your second, this thing 1,2, right, and H has been added here, and that's it. That's your first product. This is the 1,2 addition product, and the second product is like this. This is the 1,4 addition product. That would be happening if you are adding HBr. Similar to the case that we have seen previously, this time we have used HBr. Now why does that happen? Why 1,2 adduct and 1,4 adduct? That is a question. For that, let us look at the mechanism of this reaction. Mechanism: dissociation of the reagent. What is the reagent here? HBr. Step number 1, dissociation of reagent. Okay, and reagent, let me write it as reagent. Okay, HBr, that gets split into H plus and Br minus. Which is the electrophile? No doubt, it is H plus. Step number 2, what would happen now? The electrophile will attack the alkadine. Let us see. Step number 2, attack of electrophile and formation of allylic carbocation. Let's see and understand what allylic carbocation is. We will come to understand that once we see the attack. So this is our substrate, that is your 1,3-alkadiene. That's right. This is the 1,3-alkadiene, and now let H plus attack. Fine. So what can happen now? It can take from this. Okay, let it take from this. Correct. If it takes from that carbon, hydrogen has been, see, H plus has taken electron pair from this carbon. Okay, suppose, then positive sign will come on this carbon, because there is loss for this carbon, because this electron pair as such was given to H plus. For this it is not a loss, because its electron is still here. The electron that was given was his electron. So this carbon is at loss. So that becomes positively charged. Right? So this is the current scenario. So you got an allylic carbocation. This is a vinylic carbon, which is vinylic carbon is that carbon which is directly attached to double bond. So this is a vinylic carbon. This also is a vinylic carbon because it is directly attached to double bond. What is an allylic carbon? This one. Okay, it is attached to a carbon which is attached to double bond. So this is the allylic carbon, and this is an allylic carbocation. Now what would happen? This is structure number 1 for the carbocation. Okay, this is a carbocation. Now what would happen? This bond will go here, and what you get? You get this thing like this. Let me write it as CH3. Okay, as simple CH3, CH, CH, just let me rub it because of lack of space. This is CH3, CH, double bond CH, H, H, and positive sign comes here. So you get this structure for the second structure for the carbocation like this. When this electron jumps here, it would be, the positive sign would come here, and its positive sign will be negated. So now the positive sign come here. So there are two options. There are two allylic carbocations here. This is also an allylic carbon. This is also allylic carbon. In the first structure, positive sign is on this carbon. In the second structure, the positive sign is on the fourth carbon. Right? This is on the second carbon, this is on the fourth carbon. Now if Br minus attacks, it can attack at this carbon. If it attacks at this carbon, what will be formed? 1,2 adduct will be formed. If Br minus attacks in this carbocation, in this structure of the carbocation, then what will be formed? 1,4 addition product will be formed. Right? We will make it form. Okay. Let me write the carbocation, the resonance hybrid of the carbocation. Resonance hybrid is the hybrid of these two structures. It's a combination of these two structures. This is actually resonance taking place. Let me write the resonance hybrid, the resonance combination of these two structures here. Fine. So that is, this is CH. From here it's starting, right? and this is another CH, right? And this is CH. This bond sometimes breaks, sometimes doesn't, right? Sometimes the bond is here, sometimes the bond is here, right? And now look at the stabilization, the resonance stabilization of the carbocation. Look at the resonance over a large surface area, it is getting stabilized, right? So its formation is highly favored, right? Because it's stabilized over a large surface area. Now there are two chances. Either positive charge may be on the second carbon atom, as we said, on the allylic carbocation, or on the allylic carbocation the positive charge may be on the fourth carbon atom. Now if Br minus attacks this one, okay, let me rub this. This is just for this thing. Step number 3, attack of the nucleophile. Which is the nucleophile here? Br minus, correct. Attack of nucleophile, that is Br minus. Now, if Br minus attacks this structure, then what would be the product? This would be the product. Right? That is the 1,2 adduct. And if Br minus attacks this structure, then what would be the product? Then the product would be CH3, CH, double bond CH, CH2, Br. Right? So you have formed 1,2 adduct here, and this is the 1,4 adduct. This is S3, okay? S3, 1,4 adduct. So two kinds of products you have formed, the 1,2 adduct and 1,4 adduct. And why this is getting formed? Because in the resonance in the allylic carbocation, the positive charge may rest on the second carbon atom. In case if it rests on the second carbon atom, the Br minus would attack the second carbon atom, forming the 1,2 adduct. In the allylic carbocation, the positive charge may rest on the fourth carbon atom. In case it rests on fourth carbon atom, the Br minus attacks fourth carbon atom, leading to 1,4 adduct. So this results in the 1,2 adduct and 1,4 adduct in addition reactions of conjugated dienes. Dear students, this is similar to the case we have seen earlier, nucleophilic substitution reaction at allylic carbonate, allylic carbon atom or allylic substrate. In that video also we have seen how 1,2 adduct and 1,4 adducts are formed due to resonance. Please do refer that video and you will get more idea on how 1,2 adduct and 1,4 adduct are formed there due to resonance. Dear students, I hope you have understood this class. If you have understood the class, please do not forget to subscribe the channel. Do like and share it. Thank you very much.